to talk about orbitronics, the prospects and challenges. And that's kind of a new field that we believe is relatively exciting and very promising. And I will try to explain to you why we think that way. To understand that, let's first take a look at the data that you have all seen many times. And that's the realization that we live in a digital universe and that we produce more and more data. And that's actually a big problem, not only because this leads to high energy consumption of the whole information technology, but also material-wise, this is not really sustainable. And this situation continuously calls for novel concepts for energy efficient IT and new ideas of how we could do things differently, which would change this trend, which we don't like, certainly. Now, if we look at the progress of our handling of data, for example, then you have to admit that we have made dramatic progress. And that's how 5 megabytes of data looked in 1966. And you have to admit that up to now, so nowadays it looks a bit smaller, so we're a bit more comfortable with the data at this point. And you have to admit that also this comes as a benefit of having a firmer grasp at the nanoscale, at the properties of systems which actually live on a nanometer or on an angstrom scale. That is the success which we associate with the quantum mechanics. But here in particular in technology, we also have to underline always that some of the victories that we had here can be associated with the physics of the spin of the electrons. A particular example here is this magnetic hard disk, where we say we use the up or down magnetic domains to store bits of 0 or 1, and we use spin transport phenomena to read off the state of these domains, and thereby we can realize what we call a magnetic memory. Now, spintronics, that's a field of science which deals with applications of magnetism as well as with fundamental aspects of magnetism, has developed into a vast and very exciting field. Here we have, for example, the field associated with the properties of exotic magnetic materials. We have chiral spintronics, which deals with the properties of real space textures such as fermions. We're thinking of ultra-fast applications of different spintronics effects. The role of topology is becoming very prominent in combination with magnetic properties, more and more so. And since recently, we also have this field of antiferromagnetic spintronics, which is developing quite rapidly and successfully. Now, all of these fields are, in principle, if you look at it practically, they are designed so that we could solve some of the pending problems of technology. And this comes from design goals. For example, we want to have smaller, more robust, and ultra-fast bits, which we can control purely electrically and which are energetically cheap. And this poses challenges on the generation, transport, manipulation, detection, and all sorts of out of equilibrium magnetic effects. And in particular, there is a whole bunch of effects which is able, in the past 10 years or so, is speculated to solve some of these problems. And what is very nice here, or at least I find a lot of personal satisfaction in the fact, is that many of these things are associated with the effect of spin-orbit interaction. And that is because spin-orbit interaction in magnetic materials evolves on a relatively modest scale of 10 to 100 milli-electron volt. And that means that to work precisely or to make some predictions which are reasonable on such energy scale, we really had to go far and work hard to develop more and more analytical and numerical methods in magnetism, and in particular in theoretical magnetism, so that we could bring it to the level where we could conduct realistic simulations of complex phenomena in complex materials. Let me give you a first example. That's the example of the spin Hall effect. The spin Hall effect is an effect which has been studied intensively in the past less than 20 years. And it comes, actually, its parent effect is the anomalous Hall effect, which was discovered more than 100 years ago, where we know that if we apply an electric field to a magnet, then we will be able to generate a transverse charge current or transverse voltage, which is called Hall voltage, which is the effect due to spin-orbit interaction. Within the spin-Hall effect, we don't have any magnetism, and even in paramagnetic materials, we are able to separate the electrons of spin-up and electrons of spin-down on the opposite sides of your sample. Again, this is the effect which roots in spin-orbit interaction. Now, we started thinking about these things of how to calculate them a long time ago, and what we realized is that when you treat these things properly, things which you thought are not so important in studies of conventional transport effects become of crucial importance. And a good example here is the fact that we realized that the Berry phase of Bloch electrons, which live in this reciprocal space, becomes one of the key factors which determines the strength and material properties of, for example, the spin-Hall effect. So you had to get a handle on that. You had to be able to navigate in the sea of complicated things and estimate them numerically. But if you do this successfully, you can really delve deeper into these foundations of spin injection, spin accumulation, and spin torques. You can make predictions theoretically and confirm them experimentally. For example, you can predict that the spin-Hall effect should exist even in what we call PT symmetric antiferromagnets, which is intuitively quite not clear that this would be the case. Moreover, you can predict that the spin-Hall effect would operate in ultrafast domain at terahertz frequencies. Another prominent example is the effect of spin-orbit torque, which I will discuss today in greater detail. The spin-orbit torque is an effect which occurs in magnetic materials with broken inversion symmetry. And here, what we have is we have a spin-orbit interaction, we apply a current, and what happens by magic is that the magnetization experiences what we call a torque. So it wants to be shifted along a certain direction. This effect is surprising, perhaps not in its physical manifestations, but in the fact that it has been successful in efficient switching of ferromagnets, as well as in switching of staggered magnetization in antiferromagnets. There are many phenomena and different sources of this which are discussed, in particular of which one is the so-called anti-damping spin-orbit torque, where we have a ferromagnet deposited on the paramagnetic substrate, and here we excite a spin-Hall effect, and the spin current which is generated then interacts with the magnetization in the magnetic layer. Or this torque can originate in the redistribution of spin polarization of your electrons inside the magnetic material itself, for example, at the interface where the inversion symmetry is broken. Moreover, as the spin-Hall effect, spin-orbit torque seems to be also working in the terahertz domain, which is good news because this would allow manipulation of magnetization at ultra-fast frequencies, something that we need for technology. By now, the spin-orbit torque has developed into a mature field. It is more than 10 years now, and it has been found to work in different classes of materials which are of completely different nature, metals, insulators, and so on. It has a bunch of different practical applications, and you might actually have heard about the SOT-MRAM ideas of memory. And it has a lot of legs going into different physical branches of magnetism, of solid state physics. So it is a very intricate effect, which is very exciting, very interesting, and involves a lot of complicated physics. And if you look around since recently, you might have realized that there is some sort of orbital aspect of this, which becomes more prominent and which draws some attention from the community. So how does that come about? How does orbital physics penetrate into this field of spin-orbit torque, which is allegedly working with magnetization? And let me try to explain it to you so that we enjoy this physics together. What we know about orbital magnetism. Orbital magnetism is a textbook effect. It is the phenomenon which is due to rotation of electrons around atomic cores. As a result of this rotation, an electron develops an orbital moment, which we denote here as L, and we will discuss the properties of this. Now, by the spin-orbit interaction, the orbital moment is connected to the spin of your electron, and that is a relativistic effect. Now, you also know that in crystals, very often you have a crystal field which combines the groups of your states in such a way that you don't have a formation of the orbital momentum globally. However, when you have spin-orbit interaction and you have an exchange splitting, then you can partially occupy in the solid orbitals which carry a specific value of the orbital momentum. However, what we also know is that this orbital moment, even in ferromagnets, is significantly quenched. And that means that the values that we can get of orbital magnetization in magnetic materials are normally an order of magnitude smaller than those that we get from the spin magnetization. Moreover, if you look into the theory of the orbital magnetism, you will realize that it is very complicated, which is due to the fact that the position operator which participates in L operator is unbounded in solids. And there is a lot of effort which is occurring as we speak since the past maybe 10, 15 years, which is aimed at providing a proper theory of orbital magnetism in equilibrium or out of equilibrium as well. For example, if you take a look at two most common approximations for orbital magnetism. One of them is what we call the atom-centered. That is where we evaluate the value of the orbital momentum on our Bloch states, and then we sum them up to our Fermi energy. And there is this very complicated expression, which is a proper expression for the orbital magnetization in a solid, which seemingly does not involve L operator at all. Extremely counterintuitive expression, which is moreover very difficult to integrate and to deal with because it involves these geometric contributions that I have mentioned before. If you compare what these two completely different things give you for elemental magnets such as iron, cobalt, nickel, you will really wonder whether this is something that you want to do. The question is whether all this effort is worth doing it, because obviously there is not so much difference between different approximations. However, orbitronics is a field which is developing quite rapidly. Obviously, more and more people find it more interesting and more rewarding digging in this field. And the reason for this is quite simple. It comes from the weakness of the modern spintronics, or its branch, the spin-orbitronics, to which, for example, spin-Hall effect and spin-orbit torque belong because they rely on spin-orbit interaction. That is because in modern spin-orbitronics, we heavily rely on strong spin-orbit interaction. The stronger spin-orbit interaction is, the stronger the effects are that we're talking about. That means that in our applications, we normally rely on heavy materials, and many of these materials are critical raw materials. That means that we actually don't have many of those on our planet. And one of the main benefits of working with orbital degrees of freedom is the fact that it relies on light elements. It works also with light elements such as copper or aluminum, which leads to sustainable electronics. Moreover, and we will discuss this in a bit, if you compare the efficiency of orbital mechanisms, for example, for spin-orbit torque, and consider the parameters of spin transfer torque, spin-orbit torque, and orbital torque, which we will discuss, you will see that the orbital torque is by far, especially in the energy efficiency, exceeds the expectations that you have from these two conventional effects that we are working with these days intensively. So how does this happen? I will try to explain in this presentation by drawing your attention to the fact that orbital magnetization has some exotic properties. So, as I mentioned, it does not need spin-orbit interaction, which might lead to sustainable electronics. The orbital torques, that are the torques on magnetization due to orbital effects, can be very large, and they have thereby an increased energy efficiency. Moreover, the orbital currents that we can generate in solids, in analogy to the spin-Hall effect, are very long-ranged in nature, which can bring you novel design ideas. Moreover, what is making orbital magnetism very exciting is that obviously you have seen that it couples to the lattice. It comes from the rotation of your electrons around atoms, and thereby it is sensitive to the lattice degrees of freedoms, such as phonons. But also it naturally couples to other excitations in your magnets or in paramagnets, such as, for example, magnons. Let's start from the first, and let me briefly explain or try to explain to you why we don't need spin-orbit interaction for orbital magnetism. And for this, let's take a look at what happens at a surface, a simple non-magnetic surface. Let's take a Bloch electron, which propagates with a certain Bloch vector on our surface. And let's now assume that it has a certain angular momentum, which is perpendicular to it. If you put it in a simple model, which allows for the formation of L, such as, for example, SP model of your solid, you will realize that this Bloch state will be deformed and it will develop a polarization which is pointing out of the plane of your surface. It will be of this kind, and it will couple to the surface gradient at your surface and the electric field which is generated there. This will lead to the energy of this interaction between the P and between the electric field. That is known as the orbital Rashba effect, which we like very much because it looks very much like the normal spin Rashba effect. You have this typical shape of the Hamiltonian, and the strength of this effect is driven, however, not by spin-orbit interaction, but by the crystal field effect, given by the so-called orbital Rashba constant. As a result of this Hamiltonian, you will have a splitting of your P states, for example, in the surface P system, such as bismuth silver, into large chunks of bands, all of which have specific values of orbital angular momentum. That is very exciting. And one of the consequences of this would be the creation of chiral orbital textures at the Fermi surface or in the reciprocal state of your states, all of which have some angular orbital momentum pointing in some direction. What is nice is that this orbital momentum actually has no upper limit, unlike the spin, which we know is limited by the fundamental principles of quantum mechanics. The orbital magnetism is not so restricted in this sense. And that makes it also promising because you can really create large effects here. Now, if you understand this orbital Rashba effect and you understand this asymmetry in orbital distribution on your Fermi surface, then immediately you can probably say intuitively somehow that if I apply a current in this system, I will change the occupation of left movers and right movers. I will move some of these guys into this region. And that means that I will be able to develop a macroscopic orbital magnetization. That is what we know as an orbital Rashba-Edelstein effect, or which should be properly named as the current-induced orbital magnetization. Another effect which can be used to create this non-equilibrium orbital properties, orbital currents and orbital polarization, is the orbital Hall effect. It is a brother of the spin Hall effect. And here we take a solid, we apply an electric field to it, and we observe a motion, transverse motion of the orbital angular momentum. In fact, this orbital Hall effect has been known for some time, roughly as for the time as the spin Hall effect has been known. And it is known as the very prominent effect in solids. The theory of it also tells us that there is a special type of Berry phases or novel topologies which can be associated with this. And this is something which is also developing since recently, in particular taking the material class of transition metal decalcogenides. And here I take an example of this decalcogenide, which is europium disulfide, to show you that in a complicated material, you can have all of these effects prominent together. For example, you can have the anomalous Hall effect, you can have spin Hall effect, and you can have an orbital Hall effect at the same time. So in reality, you can use all your tools and your theoretical means to do some material science, to engineer the strengths and interplay between these different effects that you want. Now, so far, I've given two material examples, and they are both very heavy elements. One of them has europium, the other one has bismuth. Let's turn to the third example, which probably underlines or demonstrates the point of light elements more clearly. This is the copper oxide. In reality, copper oxide or oxygenated copper, I should rather say, is a very complicated material. But in the past years, we have modeled it simply, as simple theoreticians would do, by considering just the effect of oxidation at the surface, taking a copper slab and putting oxygen on top of it. But I think for general conclusions that we made out of this, this is completely sufficient. And the reason for this is the fact that we observe a very prominent orbital Rashba effect in the surface, which is completely unexpected. If you look at the magnitude of orbital magnetism that you are able to achieve in these light states without spin-orbit interaction, it is really kind of astonishing. Now, using the logic that we can use this for generating non-equilibrium orbital magnetism, let's test it. And in fact, if you apply an electric field to this simple system, you will observe a colossal current-induced orbital magnetization, as well as an orbital Hall effect, which are by far superior to what your spin response, which is sensitive on spin-orbit interaction, gives you. So mark that the spin properties here are scaled by a factor of 10. In fact, if you look at the magnitude of the orbital Hall effect, you will realize that it is comparable to the strength of the spin Hall effect in platinum. And that is certainly good news. That is quite interesting. And if you're a practitioner in this field, you would immediately think, okay, so I have to try to use it somehow to control the spin in my magnetic materials, because you know that a large part of research in spin orbitronics is finding materials which give you a large spin Hall effect, which you can then use for example, large spin orbit torques on your magnetic materials. So the question is, how do we use these orbital effects to manipulate the spin properties? That's the question I would like to ask and answer. To answer this question, let's look at the fundamentals of this problem. What we want to change in reality is the direction of the exchange splitting of electronic states inside the atom. That is what our magnetization stands for in a magnetic material. That is something that we call an exchange field, which splits your electronic states into spin up and into spin down. The only thing which couples to it in your electronic Hamiltonian, in your Hamiltonian of your solid, is the interaction with the spin, with the Pauli matrices, with the spin polarization of the electrons in your solids. Now, due to spin-orbit interaction, the orbital properties are, of course, also entering, and they are able to modify the spin polarization of your states, thereby exerting torque on your magnetization. Now, you can imagine that in a situation where you have an orbital moment misaligned with the spin of your electrons, there should be some sort of complicated dynamics. And as a result of this, we will be able to change the spin polarization and influence the direction of our exchange field. It should work similarly to the effect of spin torque, where we use a spin Hall effect, for example, to inject a spin current into magnetic part of our system, which then interacts with this magnetization and they change each other. In case of the orbital injection, for example, by the orbital Hall effect, we inject an orbital current into our magnet, which then interacts with the spin polarization of electrons in a ferromagnet, which in turn exert a torque on the magnetization of my ferromagnetic material. The key quantity here is in a ferromagnet. That is what we call an orbital to spin conversion efficiency. That is the strength with which the excess of orbital magnetization can induce the change in the spin polarization of my ferromagnet, which I take out of equilibrium. Okay, so this should work. That was the idea. And let's take a look at this copper oxide again. So part 2. We know that copper oxide produces large orbital currents and it has a very gigantic orbital polarization. So we have to harvest these currents somehow. The most efficient way to do this would be to use a material which is able to take these orbital currents and transform them into spin currents. For example, you could take very same platinum and try to inject these orbital currents in there. Then, once these currents are transformed into spin current, you can inject them into ferromagnet and try to switch the magnetization there. And that is exactly the setup of an experiment that we have been researching or conducting and explaining together with the Chloe lab. Here, you take this fantastic copper oxide, you insert a small layer of platinum, and you use a ferromagnet underneath. So what happens here is exactly what I said, or at least we believe that's the case. We exert an electric field, we enhance the orbital currents here because platinum has a very large orbital to spin conversion, and we are thereby able to exert a torques on this ferromagnet, which are larger by a factor 16 to the situation where we don't have copper oxide on top of this platinum layer. This is a very large number. If you think about it, you have your platinum system. Everybody is very familiar with it. You throw a little bit of this not important copper oxide, which you think will do nothing. And in contrast, it gives you a 16 times enhancement of the spin orbit torque, which you feel far away from this copper oxide. This effect of this orbital torque, so let me call it now, it's an orbital torque, because here it is based on generating and manipulating the orbital magnetization of my system. It has a twin, which we also call an orbital Rajma-Edelstein magnetoresistant. Here, we take the same copper oxide and we put it on top of a permalloy. And when we apply an electric field, there will be an orbital current diffusing into permalloy. And of course, in one case, it will be absorbed by the torque, and in the other case, it will be reflected, depending on the magnetization direction of your permalloy. This you will feel in the diagonal resistivity, and this is exactly the essence of this orbital Rajma-Edelstein magnetoresistance. Very nice effect, no doubt. However, there is one interesting feature that we have noticed when we were doing this. When we were trying to explain this with some sort of diffusion models, we realized that the scale of penetration of this orbital current into permalloy is an order of magnitude larger than that of spin in a system where you use platinum and not copper for injecting your spin current into permalloy. That is very surprising. And the question here is actually, how does that happen? What is the physics behind it? Because this seems A, unexpected, and B, quite promising. That is very nice if we can inject our orbital currents and they can propagate for tens of nanometers in a magnetic material. The fact is that physics of orbital magnetism in magnets is very complicated, and it is more complicated than, for example, in copper oxide. And the reason is that in a ferromagnet, we have an additional player. We have a magnetization. So let's take a look at this simple picture which I drew in the beginning of this talk. We have a magnetization and we have an orbital splitting of our states. Only one of these states is occupied, so the Fermi energy is somewhere here. Now, what happens when we switch the magnetization from up to down? The orbital magnetization by the spin-orbit interaction will also flip sign. That means that this state will go down and this state will go up. And this will happen by the emergence of so-called while points, which we call the mixed while points, to underline the nature of the fact that they have topological meaning in the mixed space of the Bloch vector and the magnetization direction. In fact, these mixed while points, they occur regularly at the phase transitions, for example, between normal insulators and churn insulators in different models and in two-dimensional materials. Now, if you look at the change of the orbital magnetization in some of these models, as you do this switching of magnetization, yes, it changes sign as you change the magnetization direction. This is the angle of your magnetization direction with the normal to the surface. However, if you look at the response of your current-induced orbital magnetization, you will realize that it is A, gigantic, and B, it is also sensitive to the topological nature of this while point, to its charge. And this is quite nice because this tells me that current-induced orbital magnetization serves as a marker of topological transitions in magnetic solids. What is very interesting is that in the same type of systems, we have been also predicting that these while points are the reason why we can have really gigantic torques even in insulating materials. And if you think about it, it does not necessarily ring a bell. Okay, so we have large orbital magnetization in response to current. So we have a large torque. How to reconcile these two findings? And in fact, you can do this. And doing this is extremely insightful because it lets you understand what happens microscopically. To do this, let's write down some fundamental equations, and these are the continuity equations. So we take a look at the density of our orbital angular momentum in space and in time, and at the density of spin angular momentum in space and in time. And you can write down these equations where there are basically two fundamental terms. One of them is the influx of angular momentum into a specific part of space, and the other one is loss of this angular momentum on the torque on your magnetization. We're interested in the spin because we're talking about torques on magnetization, on spin magnetization. And if you take a look at what this torque decomposes to, it has two terms. One of them is the exchange torque. That's the torque that we're interested in. That's the torque that we measure experimentally because it stands for the interaction between the spin of my electrons and the exchange field, which, as I explained, is the main quantity here. The other torque comes from spin-orbit interaction, and that is what we call a spin-orbital torque. This is the torque which penetrates the equations for L and for S on equal basis. It couples these two. It allows for transmission of orbital angular momentum into spin and vice versa. Assuming a chain of approximations, you can even write down an approximate expression for the spin orbital torque, which looks exactly like this precession term that I have been also showing a couple of slides ago. Now, if you assume that you're in a system where there is no influx of external spin angular momentum, then you realize immediately that all the torque on your magnetization is given by this excess of orbital momentum in your system, which you create. That means that in 2D limit for two-dimensional systems, spin-orbit torque is purely orbital in nature. And that's important to realize and to understand that orbital torque is actually the major player in the physics of two-dimensional magnets. Of course, this can be more complicated than what I said because your two-dimensional materials can be relatively complicated. For example, they can be layered. Take a look at the example of this iron germanium telluride, which in its normal phase consists of two types of layers, A layer and B layer in the unit cell, repeated along the Z-axis here. Now, the whole system has an inversion symmetry. However, that is not so for each of these layers separately. And that's why we're talking here about hidden or layer-resolved properties, in particular torques. Let's take a look at this FGT with magnetization close to the out-of-plane direction. And let's take a look at current-induced orbital magnetization of your states. You see, it is gigantic. It is very prominent. However, if you do the integration in the Brillouin zone, you realize that many of these contributions cancel. And in fact, for this direction, it is the transfer of spin angular momentum among these two layers which does the torque on each of these layers. The situation changes when I put my magnetization into the plane, where the distribution of orbital magnetization is completely different. However, here the contributions add up, and the torque for this situation is purely orbital in nature. So, in principle, by using magnetization direction, you can realize this orbital to spin crossover in the natures of, in the origins of your spin orbital torque. Now, these degeneracies, these mixed Weil points, they're actually fantastic. And the reason for this is the following. They do not only provide a large response, for example, of orbital magnetization and spin orbit torques, but they also have slow dynamics. And what I mean by slow dynamics here. Let's take a look at an example. Let's take a look at cubic lattice of T to G orbitals, and let's look along the KX direction somewhere. What we have here is a crystal field splitting, and here you have a degeneracy between these states, which may be slightly lifted by spin-orbit interaction. So what I do next is I create out of these two states a state which is polarized along X and which has the value of +1 at time equals 0. And then I let the system propagate in time by solving the Schrödinger equation. And what I realize is that this Lx of +1 decays very slowly in time because it has no other place to go. It has nowhere to scatter. And in this sense, these kind of points, they also serve as orbital traps where your orbital polarization can survive over very long times and over very long distances, because you can inject your electron at this k and it will propagate into your solid while at the same time pertaining this value of orbital polarization. And in the magnetic material, this is unique because this is in contrast to what happens to spin injection. Here, the injected spin will start oscillating around your magnetization, scattering, and it will decay relatively quickly away from the interface of your injector with the ferromagnet. Interestingly, you can even support these sketchy pictures by explicit calculations. And here you see a system of cobalt iron deposited on chromium, where chromium is non-magnetic. And if you evaluate the response of your orbital magnetism along x direction as you apply your field along x, you see this very slow decay over 40, 50, and it disappears somewhere at the 60 layers of your ferromagnet. You can also look precisely at where this effect originates from, and you can clearly see this kind of degeneracies where the effect is the largest, such as, for example, here or here. That is, of course, a very nice finding, and this long-range nature is extremely interesting. However, it also has repercussions for the orbital torques in your magnets. That has an impact on how the torque would behave as a function of the thickness of your ferromagnet. Let's take a look at our calculation, and let's see, as we increase the number of ferromagnetic layers, how does the overall torque on your magnetization change? It actually changes sign as a result of competition between orbital and spin parts of your torque, and then it continues to increase steadily with the thickness of your ferromagnet. Completely counterintuitive behavior, which you would not be able to understand if you didn't have to assume that something is really long range here. And as I showed you, it is the orbital currents, orbital polarization in the system, which is long range. And very surprising, but recently there is more and more experiments which actually confirm this behavior. An example here is nickel deposited on titanium, where we observe a very similar behavior in the torque. You can extract the diffusion length or the decay length of your orbital currents, predicting it to be of the order of, for example, 50 nanometers. Absolutely unthinkable for nickel diffusion length, if you ask me. The corresponding effective orbital Hall angles you can also extract, and they are also very large. At least you have to hunt for such angles in the normal spin-orbitronics domain. The scattering here also seems to be very challenging to understand because it deviates from the physics of normal skew scattering that we know for the spin Hall effect or for the anomalous Hall effect. But I leave this discussion to some other time. One aspect which I would like to emphasize before moving on to the last part of the talk is that in the design of orbital properties, ferromagnetic properties really matter. It really matters which ferromagnet you use. Let me give you an example of how this works. Let's say we take niobium and ruthenium, where theory predicts that there is a very large orbital Hall effect, in particular much larger than the spin Hall effect that we would expect theoretically in these two materials. Now, what I want to emphasize is the drastic role of orbital to spin conversion in a ferromagnet. We inject this current into a ferromagnet and something happens there. So we have to transform this orbital current into spin. Now, we know that nickel is a material which actually has a very large value of this orbital to spin conversion strength. And if you take a ruthenium nickel interface in such particular setup, you will indeed realize a very large orbital efficiency or spin orbit torque efficiency in this material. And again, you're able to observe this characteristic kind of enhancement with the thickness that I have been talking about in the previous slides. However, in the world of spin torque or conventional spin orbit torque, it wouldn't matter now if I would put iron or cobalt or iron cobalt boron. It should have the same large spin orbit torque efficiency. But this is not the case for the orbital effects. Here, if I take, for example, iron cobalt boron, the effect is 10 times smaller. And that is because here I have a very small orbital to spin conversion strength. Now, playing with these things, engineering them and cooking up different converters also allows me to claim that this is orbital transport that I have here. Because I can use again this idea that if this is an orbital current, I can enhance it by platinum. And if I construct such a superlattice where I kind of compensate the spin Hall effect coming from platinum in here from both sides, I can enhance this orbital current coming from ruthenium, which this iron cobalt boron does not see, into spin current of gigantic magnitude, which switches the magnetization in iron cobalt boron. So a lot of avenues for material research, for playing around and playing over orders of magnitude in the spin orbit torque efficiency, as well as the penetration depth of your orbital angular momentum. Very exciting, very promising. One last aspect about magnets and orbital magnetism that I would like to highlight in my talk is the fact that magnets can be even more complicated than that. Magnets can be non-collinear. In many of our magnetic materials, which are also, for example, intensively studied in Halle, in your institutions, are the non-collinear magnets, which exhibit non-collinear magnetism in their ground state or as a result of fluctuations. Now, orbital magnetism plays out also here. In non-collinear magnets, if you imagine some non-collinear triplets of spins, for example, there is an additional contribution to orbital magnetism, which we call topological orbital magnetism, in analogy to the topological Hall effect, for those who know what it is, which comes from this non-local jumping of an electron around this triplet of cores. This is the effect which is promoted to the by the non-collinearity. It is proportional to non-collinearity, for example, to the scalar chirality between the triplets of spins. In reality, the resulting orbital magnetism is proportional to chirality, to the crystal structure, and also to what we call orbital susceptibility. So this chirality acts as an effective magnetic field, which this susceptibility feels and transforms into orbital magnetism. It is a very efficient magnetism because the effective magnetic fields of non-collinear magnets can be really gigantic, of the order of thousands of Tesla, and the corresponding orbital effects can be very large in real materials already without spin-orbit interaction. This is something which has been also been promoted and very interesting to observe the progress in this field. For example, the discovery that this orbital magnetism can mediate interactions between spins and more phenomena of this kind, which I'm not going to discuss here. The question I'm going to ask is whether we can promote these ideas in fluctuating magnets. For example, you can imagine some elementary excitations of your magnetic materials. And intuitively, if you look at the spin wave in your material and you sit somewhere here, you may realize that locally, all the time, you feel a chirality or scalar chirality of the neighboring spins in this material. So let's test this idea. And for this, I have to say right away that in order to feel this effect, you need it to be non-vanishing over your solid. And this happens only on special types of lattice, for example, honeycomb or kagome. And if you construct a simple possible magnonic Hamiltonian on such a lattice, and you try to take a look at the chirality of your magnonic bands by constructing a proper operator which captures or which is sensitive to the chirality, you will realize that your magnonic states, your magnonic band structure, even in ferromagnetic in the ground state systems, acquires a net chirality which can be felt by your electrons. This is the case, for example, for this model Kagome lattice, but also, for instance, in manganese-3 germanium, the effect is there and it is quite large. This chirality, which the magnons would exhibit, as you increase the temperature, you can integrate over your magnonic structure and you can say how it behaves with the temperature in your material. For example, you can use temperature to have more chirality in your sample. And if you change the parameters in your magnonic system, you can change the sign of the chirality in your system. This is a very interesting tool to generate chirality and actually engineer its properties. Now, would this result in magnon-mediated orbital magnetism? And my answer is most probably yes, or I believe that it should. I believe that it must. However, we have to provide some evidence for this. And in the next slide, I want to discuss an experiment which could be a proof of the fact that something like this is happening. And moreover, I believe that it is not only happening in this material, but it is happening in many materials. We were just not really looking at that until now. Let's take a look at so-called copper 13 BDC material. That is a two-dimensional material, which is a honeycomb lattice. And this is material which is known for a long time in the field of topological magnonics because it exhibits this topological magnonic gap. It is a so-called topological magnonic insulator. Now, if we take this material and we construct the band structure of magnons in it, we can calculate the chirality. And you see the chirality of magnonic bands marked here according to the sign and magnitude with this red and blue. Now, according to the theory of topological orbital magnetism that you have seen a couple of slides ago, we can translate this chirality by using this orbital susceptibility into the effective orbital moment of your electronic bath, which is subject to these fluctuating magnonic excitations. What I can do next is I can predict what happens in the system with respect to integrated orbital signal when I change the magnetization direction in my sample and when I increase the temperature in my sample. And the prediction for these materials are the following. If I have an in-plane direction, if my field is in-plane, there is nothing interesting happening with temperature. The effect is zero. However, if the magnetization points out of the plane, there is an enhancement of orbital magnetism with temperature. So the overall magnetization should, in principle, increase. The enhancement is not very large. However, there is a sensitive quantity, which is quite sensitive to the orbital magnetism, for example, in this system. That is the G factor. So if I'm able to measure the G factor in this system precisely, this evolution in the orbital magnetization, in principle, I can track. My prediction is that with increasing temperature, the G factor has to increase for the out-of-plane magnetization, but it should not increase for the in-plane magnetization. And this is exactly what our experimental collaborators, that's the group of Wei Zhang in the US, observed by measuring the G factor in this system. So what you see for the in-plane field is that the G factor decreases a little bit over the temperature range, which is gigantic for this material. And that is the behavior you expect, because with increasing temperature, also the spin orbit effects, which influence predominantly this situation, they become weaker. On the other hand, for the out-of-plane field, there is a drastic increase of the G factor in your system, which is in accord with this magnon-mediated orbital moment that we predict by referring to our theoretical tools. Now, this is quite interesting. And if it is true, and as I said, I believe it is true, that is good news for the field of magnonics as well. Because, for example, here I can imagine that I can use a temperature gradient to drive various magnon currents. And these magnon currents are known to scatter. And you can generate transverse magnon currents. And according to this theory that I have just laid out, these magnons should drag an electronic orbital momentum with them. And in particular, you can have a transverse scattering of this orbital angular momentum, which we call an orbital Nernst effect. This would be a magnonic transport of orbital angular momentum, which falls quite uniquely into this area of non-equilibrium orbital currents. This is a very nice effect because theoretically we have, of course, described it. It's very sensitive to the topology of your states. It is very large. It can be competing to the spin Nernst effect. And in particular, it can also drive magnonic torques on your ferromagnets if you use the magnetic currents to inject this angular orbital angular momentum into ferromagnets and transform them into torque there. But this is something which still awaits experimental observation. Here I come to my conclusion slide, or my challenges slide, and there are quite a few in this field. That is due to the fact that orbital motion is actually quite deeply rooted in A, electronic properties of your material, but B, also in the structural properties of your material, not even talking about the magnetic properties of your material, as you have seen. It is a phenomenon which exists at the junction between different known effects and different known fields and branches that we have been having so far. In order to make this field more mature and to have further advances in this field and talk about some technological applications and maybe some practical manifestations of that, we still have to do a lot of extensive material research to optimize orbital properties. What we don't understand, or what is a very poor theory of at the moment, is the orbital scattering theory. You have all heard, and Halle is actually a well-known center for scattering theory in magnets. We have a lot of understanding, a lot of intuition when it concerns charge scattering, when it concerns spin scattering. There, for decades, we have been calculating these things. However, orbital scattering appears as something which we do not really understand, and we actually haven't worked on it so far. And this is a key aspect which allows us to do proper engineering and understanding of things. On the exciting part, orbital magnetism, as I said, is a junction between different fields and between different sides of your solids. Phonons, magnons, electronic excitations. And perhaps it is a very unique link between these excitations to serve as a sink and source for transmitting orbital angular momentum, or generally angular momentum, between different systems, different baths of excitations that can simultaneously exist in your excited solid. Very exciting, completely unexplored, and probably gigantic technological relevance. If you especially think about the fact that you can excite your system already by excitations which intrinsically carry angular momentum, such as laser pulses or vortex beams or even acoustic waves. So we're talking about a big mass with an orbital momentum in the center of it, which combines optics, which combines mechanics, magnetism, magnonics, and all the fields that you know. And we think it's just at the beginning, and it is absolutely fascinating to think what kind of prospects we can achieve here given time. Okay, so I have to thank the people which have been doing all this nice work, in particular my outstanding co-worker, colleague, Dongwook Go, but also you see a bunch of other guys, Frank Freimuth, Fabian Lux, Li Chuangzhang, Tom Saunderson, a lot of other people which have been important, including our experimental collaborators, that's Matthias Chloe's lab, Jingbo Yang's lab, Young-Guk Park, Kazuya Ando's lab, and I thank all of them. This has been outstanding work, and I would like to thank you for listening to this presentation.
Thank you so much for a very exciting talk. So we have time for some questions. Can you hear us actually?
Yes, I can hear you.
Other questions in your house? Okay, Niels.
Thanks for this very nice talk, Yuriy. I have two questions. So one is about how to maximize these orbital currents that you want to generate. So my understanding is that actually to get an orbital angular momentum texture on your Fermi surface, you need to break inversion symmetry, ideally. So, or at least that's one way to do it. So to maximize this effect, then would you suggest that one could somehow maximize inversion symmetry breaking by, for instance, looking at structurally chiral materials? Would that be a way? So this is question number.
That is a very good point. And by by using chiral materials, you can not only engineer large orbital magnetism, but also the sign of it, yeah, because it would be sensitive to chirality quite naturally. And in fact, there is a lot of discussion, if you have heard, about chiral molecules. There is all this current-induced spin polarization in chiral molecules, which we actually believe to be of orbital character. Just because when your electron propagates in a chiral crystal, in chiral environment, it naturally develops in orbital magnetism. Yes. So you're absolutely right. One way to go would be to kind of optimize the properties of your broken inversion symmetry. In particular, ferroelectrics are a very interesting field to look at the interplay with orbital magnetism, but also other materials, as you said, chiral materials. Yes, I absolutely agree. Good point.
Okay, and the other question is, at the end of the day, it seems from your talk that you still need some material to convert these orbital currents into something, into a torque that can interact with a spin.
Yes.
So can you say a little bit more about what's required there? Is it just large spin orbit coupling that does the trick? Or you were also saying that nickel is somehow good at this, but it's not.
Yes. So what you need is, and this you can show from analytical arguments, is, so I call it, okay, orbital to spin conversion strands, or you can look at it as spin to orbital conversion strands, which is proportional to the spin orbital polarization and the energy into which you inject your currents. What is spin orbit polarization? That is the average of your spin orbit interaction over states at the Fermi surface. Strong spin orbit interaction is not sufficient. So what you need also a certain orbital complexity. So if you look, for example, in nickel as a function of the Fermi surface, where is this spin orbit conversion strongest, where this integrated spin orbit polarization is? At the Fermi energy, it is very strong. But in principle, since it's a magnetic material with small spin orbit interaction, it has a very complicated structure as a function of your band filling. Yeah. So having a large spin orbit interaction is not a guarantee of large spin orbit conversion. It is more complicated than that. So you need to optimize the matrix elements of your spin orbit interaction, and that is a complicated thing. So they're complicated. They're just not proportional to a constant. So if you're in the middle of the D band, or if you're at the edge of the D band, if there is some P state coming in, all of this influences your LS matrix elements.
Yeah.
If I may ask a follow-up.
I think there's Shinlang has his hand raised on Zoom. So Shinlang.
Yes. Okay. Yes. Thank you very much, Yuriy, for the excellent talk. So, I mean, I'm not a physicist. I'm more chemist. So my question a little bit more general. The first question is more regarding the spin orbital talk which you presented. How far is it still from more practical, application in data storage as you give the bigger picture, bigger vision, So how far is your, spin orbital talk, what you are developing from the real device integrations?
That is a good question. So probably quite far, just because, so the device integration depends very much on whether you can prepare materials or not, whether they can be prepared as a mass production or not. And probably here Stuart could comment much better than me. But so far, so we believe that this orbital torque could be important in many more materials that we have studied so far. Yeah. Okay. But the research is still minimal for technological applications. So you still need to optimize a material system such as, cobalt platinum kind of thing to find your guinea pig, because nickel is not very nice to work with. As far as I know, it's not easy to grow it on, for example, on ruthenium, or so you really need to go kind of epitaxial growth, and this is not technologically feasible. So that's why I'm underlying that we need more material research here. So for example, we can try to construct some trivial multi-layers of transition metals, which have a very strong orbital to spin conversion strength, put it on titanium or copper, and then you're probably much more better in business than you have been before.
I mean, this is a good point, because at the beginning you mentioned to avoid the critical raw materials. I mean, I like your material perspective there. But the transition metal, of course, is a pretty expensive metals and not really sustainable to my knowledge. So do you think which type of material class will be much more promising for the future?
I have mentioned copper oxide, but it is also probable that many more oxide materials are actually having these prominent Rashba properties, or orbital Rashba properties, such as aluminum oxide, for instance. And these oxide materials, they appear naturally. So for instance, copper, you leave it in the air, it oxidizes naturally. So you don't have to work extra on doing that. And so along these lines of oxide surfaces and interfaces, this is probably, which is probably also closer to you as chemists, perhaps molecules. So perhaps some molecular systems which you deposit on the transition metal, they could also serve as very nice orbital kind of sources. And that's something which is also very interesting to think about.
I mean, okay, just if I can ask a second question. So, but it's a short question actually. So, because you mentioned the chiral molecules, and this is definitely the interesting type of molecule we are working together, So, my question, for many chiral organic molecules, it looks like the orbital is not the chiral at all, But I mean, for me, it's difficult to understand whether the orbital is the chiral or just the molecular geometry or topology is the chiral.
So I think
have any insight there?
The key word here is that it is out of equilibrium. So as a chemist, you're probably not used to working with currents or with electrons propagating in molecules. But what happens is, so yes, there are some classes of molecules which develop some sort of spin properties even without applying voltage. So you put a molecule on the surface, there is some magnetic signal there. So one can discuss why this happens, and one of the things is some sort of uncompensation. So if you look at your molecules, and this is also known from carbon nanotubes physics and so on, you always have uncompensated, so often you have uncompensated states. So electrons which are not paired. And these electrons can develop, they have some spin polarization, they have some orbital polarization. So when you combine systems which are not having, which are kind of unpaired orbitals with surfaces of transition metals, I believe magnetism can occur there naturally. But another class of effects is where you apply the voltage. And here, your wave function changes. So you can think of it as an electron moving from one side of the molecule to the other. And as it does so, it can acquire an orbital momentum. So let's imagine you have a DNA and your electron has to move through it. It will move like this, right? And if you have a DNA of another chirality, which hopefully we don't have so much of it, then it will move in a different way. So this corresponds to different sense of orbital motion.
Okay, great. Thank you so much.
Oh, thank you very much for a very nice talk. I'd like to ask a question, a very simple question. So if you eliminate the crystal field, you could do that in a liquid. So could a current of ions carry significant orbital angular momentum?
That is a good question. So I mean, your ions, so they can have their own orbital momentum, probably. So okay, let's first consider electrons. Let's say there is no crystal field. Then an electron can have, so your solid is kind of diffuse, it's a liquid. Electrons still have orbital momentum due to motion around the ions. That's just pure quantum mechanics. And if you use those electrons to move from one place to another, they will probably also carry an orbital angular momentum with them. However, what is more interesting is to having some sort of ionic excitations, which are of phonon type. So if you excite specific excitations, vibrational of your ions, then even ions can carry orbital angular momentum, you know? Even without having any intrinsic orbital momentum themselves.
So you think they could carry a big current of orbital angular momentum?
They could. I suppose they could.
Has anybody looked at that?
I am not aware, so I cannot say.
I'm a bit confused. At the very beginning, you talked about Berry phase effects and electronic features of the electronic structure, intrinsic effects that could give rise to interesting phenomenon.
Yes.
And then your discussion appeared to be more about extrinsic scattering. So angular momentum in your calculations, intrinsic. But
well, in our calculations, we actually don't have a lot of extrinsic effects. So these things that most of the calculations I show, they are intrinsic. So they're Berry phase driven.
I thought you did mention, you talked about skew scattering, which of course.
Yes. So some of the data on tungsten samples, we don't know what it is. We're not even sure it is skew scattering. It is just that the data does not scale in the way that either intrinsic or skew scattering would. It is somewhere in between. And in principle, if you look at the theory of anomalous Hall effect, you also have all these strange scatterings rates and very non-trivial dependency relation between diagonal and transverse conductivity, which can also be reproduced experimentally and theoretically. And the same is probably true for orbital angular momentum. So when you have complicated solids with disorder in them, then you can have also effects of skew scattering.
Okay, thanks a lot. Fantastic talk.